Okay, I want to go over first of all the stuff that you were doing last lesson when my Wi-Fi went up the spout. Okay, so we're just going to whip through this stuff here. Right, questions in chat if you want to ask. Right, first bit is things that you should know. So we should be happy with this table here showing the comparison between the subatomic particles that you need to know about, so protons, neutrons and electrons, and we can apply that information here to how symbols appear on the periodic table. Okay, so we've got a mass number and a proton number or an atomic number. Okay, so if we're looking on the periodic table, for example, at uranium, uranium is uranium because it has an atomic number of 92. It has 92 protons, and you can see that here in this diagram. And we know that the mass number, the big number up here, the mass is made up of protons and neutrons added together. So the big number here represents the total of protons, which we know is that number, and the number of neutrons that we don't know directly added together. And here I've got two isotopes of uranium. Remember, an isotope means the same element, and therefore same proton number. But a different mass, and we explain the different mass because thanks to James Chadwick we know about neutrons. So different mass is only down to different numbers of neutrons. So if we were going to write the symbols for these two isotopes of uranium here, okay, they're both symbol capital U because they're both uranium. They've both got 92 protons. Their atomic number is 92. But when you see it written like this, the number is the mass here. Okay, or we could say 92 plus 146 equals 238. 92 plus 143 equals 235. In physics we'd say uranium-235, uranium-238 are the isotopes of uranium. Both of these are unstable and radioactive, so where that is the case we can also say that they are radioisotopes. So isotopes exist, not all of them are unstable, but if they are unstable and break down and emit radiation we can call them radioisotopes. Uranium-235, uranium-238 are radioactive because over time they randomly break apart and emit a radioactive particle. Okay, so we've seen already that we know there are alpha particles and we know there are beta particles that can be given out by these unstable atoms that break down randomly and change. Here you've got the three isotopes of carbon. You can see that carbon-12, carbon that's made up of 6 protons and 6 neutrons in the nucleus, is by far the most commonly occurring isotope. Okay, and we'd write its numbers like this. This isotope of carbon makes up just over 1%. Carbon 13, it's carbon because its atomic number is 6. Its mass number is 13 because it's got one more neutron. And this isotope here is carbon. Its atomic number is 6. Its mass number is 14. Carbon 14 has 2 more neutrons than carbon 12. This isotope is radioactive and gives out beta radiation. Okay, it is a radioisotope of carbon. This is the carbon atoms that, if you watch an archaeology program, that they use for carbon dating. We can work out how old something is, yeah, if it contains carbon, and by looking at how much carbon 14 is present. Okay, look, we know that 0.1% of the carbon in something is carbon 14, but this stuff breaks down. So the smaller and smaller the proportion of carbon, which is carbon 14, in an object, like a Roman sandal or something that you've dug up, okay, the older it is. Right, a few key things that you need to be able to do here. Right, so I know what an alpha particle is. We need to know what one is. So when we write alpha, there's the Greek letter, we know that an alpha particle is made up of 2 protons and 2 neutrons. Okay, so if we were going to put its numbers on, it's got 2 protons and it's got 2 neutrons, so its mass is 1, 2, 3, 4. There aren't any electrons. It's not an atom. It's part of the nucleus of something that's broken apart. So it has a charge. It's 2+. Notice it's the same as a helium nucleus, but it's not helium because it hasn't got the electrons around it. An alpha particle is equivalent to the nucleus of a helium atom. Okay, so that's quite easy to understand, that we know the nucleus is made up of protons and neutrons. If something is radioactive and it breaks apart and a particle made up of 2 protons and 2 neutrons stuck together gets fired out, the nucleus is getting smaller by 2 protons and 2 neutrons. Okay, the next thing to make sure you understand is what a beta particle is, which is a little bit trickier. So it's easy to know what it is. A beta particle is an electron. Okay, and we know that electrons have a negative charge and a tiny mass that is so small compared to a proton or a neutron that we can ignore it, a negligible mass. The tricky bit is to explain where these beta particles have come from. And I'm going to show you, we represent beta particles like this: negligible mass, effectively 0 for the mass number, and we write a beta particle and say that its proton number is -1. All right, now we're going to explain that using this section here. So how can beta particles come from the nucleus? So we know there are no electrons in the nucleus. We've learned that they're in the shells around the outside. So that doesn't make sense. You should be asking, how can there be a beta particle coming from the nucleus if there aren't any electrons in the nucleus? So we're going to explain it like this. Okay, we're going to think that when beta particles are emitted, a neutron is becoming a proton. And we're going to think of the neutron as being like a proton with all its positive charge, and teamed up with that tiny negligible mass, whoops, of an electron sitting with it. So a neutron is neutral because it's got positive charge and negative charge, and they're cancelling each other out. When the nucleus of something which gives out beta particles breaks down, this electron here gets fired out. Here it is. And we call that a beta particle. A beta particle is an electron that has come from the nucleus, and that means that the neutron isn't neutral anymore because it's fired out this electron and it has effectively changed into a proton. So during beta decay, during radioactive decay with beta particles, neutrons become a proton. A neutron becomes a proton. So the proton number is going to go up, but the mass is going to stay the same. When a beta particle is fired out, the effect on the atom is that its proton number goes up by 1, but its mass will change the same. It will not change, it will remain the same. Okay, let's look at how we do these equations. All right, so when you see them in the exam, you'll see that we've got part sum of an equation. So we're saying uranium-238 is an alpha emitter. Uranium-238 emits alpha radiation. The atoms of uranium-238 are unstable. They randomly break down and fire out an alpha particle like this. So when alpha decay happens, the proton number is going to go down by 2 because alpha particles have got 2 protons, and the mass number is going to go down by 4 because alpha particles have a mass of 4. So you can see that example here. You've got thorium, element number 90. Its mass is 228. The mass number has gone down by 4 to 224. The proton number has gone down by 2 because its nucleus has lost 2 protons and 2 neutrons. Thorium, element number 90, has changed into radium, element number 88. Okay, so if uranium-238 is doing the same and emitting an alpha particle, whatever's here is going to have 238 has gone down by 4, 92 has gone down by 2. We could look up on our periodic table element number 90 and we'd see it's this one. Okay, it's thorium. Uranium-238 emits alpha particles and turns into thorium. Uranium atoms become thorium atoms. It doesn't matter what this number is because their isotopes is this number 90 that identifies the element as thorium. Okay, so here, okay, you've got thorium, and here you've got thorium, and it's thorium because it's got 90 protons in its nucleus now. So during radioactive decay, atoms are literally changing into different atoms, a bit like old-fashioned alchemy. Okay, let's do the same for the beta decay. Remember what we said about beta particles. It is an electron that has come from the nucleus. It is an electron. So During beta decay, the mass of atoms will stay the same, whereas the proton number will go up by 1, because during beta decay a neutron has become a proton. And you can see that here we've got an isotope of potassium, potassium 40, breaking up by giving out beta radiation. The mass number has remained as 40, but the proton number has gone up by 1. Right, you can say 20 plus minus 1 makes 19. All right, so same example here, carbon 14, which we've already talked about, is a beta emitter. The thing that it turns into is going to have 14 equals 14 plus 0, 6 equals 7 plus minus 1. Element number 7 is nitrogen. During the beta decay of carbon 14 atoms change into nitrogen atoms. So we've seen our two particles now, alpha and beta. We've got rules for their decay. During alpha decay, the nucleus gets smaller by 2 protons and 2 neutrons. So the mass number goes down by 4 and the proton number goes down by 2. During beta decay, electrons are emitted from the nucleus. They weigh almost nothing, so the mass number remains unchanged, but a neutron has become a proton, so the proton number increases by 1. That's why we've got this minus 1 here on the beta particle. Right, and this diagram sums that up. Now you can see here that you've got gamma rays, but remember gamma is an electromagnetic wave. Here's the representation of gamma. So during gamma emission, there's 0 change to the mass and there's 0 change to the proton number. Gamma rays are energy like light. Okay, they're waves. So to explain gamma rays, we're talking about a radioisotope in an excited state becoming more stable by being less excited because it's got rid of some of this energy in the form of a gamma ray. Okay, so gamma emitters are becoming less energetic by these high energy electromagnetic waves coming out of their nucleus. Right, so I think we've covered alpha and beta decay. These are the ones where you have to write equations. Okay, and gamma rays we explain by saying the energy, the excess energy of the nucleus holding together is emitted as these rays like light, okay, that we call gamma rays. All right, now I'm going to talk about half-life as well, and then you'll be able to get on with today's lesson. So if you imagine, always think about pizza when we're talking about half-life. If you imagine that we've got a sample of radioactive material, okay, here it is, a pizza, and we just randomly leave it, the particles that it's made out of are going to randomly change by emitting alpha or beta particles. Okay, so I'm going to have this imaginary lump of stuff, okay, And like the graph, I'm going to say that the count rate, or the number of undecayed atoms, or any measure of radioactivity, I'm going to give it this number, 600. Okay? Every single atom in this sample has a chance, yeah, of breaking down. We cannot predict which atoms will break down because radioactive decay is random, but the chance of each one breaking down is the same. And that means that it would be like rolling 600 dice and looking at which ones land on a 6. The chance of each individual dice being a 6 is the same, but which individual dice land uppermost with a 6 is random. The chance is the same, but individual atoms occur randomly. And that means that the time that it takes to halve, okay, this amount of time will be the same every time it has to halve. All right, and you can see that on this graph, and next lesson we'll look at a model of this that will make it even clearer, that if you set off with 600 dice, you roll them and you remove all the 6s each time, the time that it takes you to have rolled for 300 of the dice to have ended up with a 6 and for you to remove them will be the same as it takes to go from 300 dice to 150 dice, or from 150 dice to 75 dice. In other words, every time the radioactivity halves takes the same amount of time. And from maths you'll know that this line here will never touch the x-axis. Okay, this amount of time is called the half-life. Okay, what is it? The time for the amount of radioactivity to fall to half its original value. Now that time could be in milliseconds, or it could be in billions of years, and anything in between. So the half-life of a radioisotope will be the amount of time it takes for the amount of that radioactive isotope to randomly become half of what it started as. Okay? Now when you are thinking about this, I talked about pizza, okay? It would be like saying, if I've had a pizza delivered, it's going to take one half-life for you to eat half of the pizza, and then the same amount of time to go from a half to a quarter, and from a quarter to an eighth. Okay, so you can say that whatever amount of radioactive material I've got, after 1, 2, 3 half-lives, there will be 1/8 of the original sample remaining. Okay, so if I said my original sample is 8 kilograms, let's say I've got 8 kilograms of uranium, which would be very dangerous. After 3 half-lives worth of time, I would have 1 kilogram remaining. Because if you cut 8 in half 3 times, 8 halved once is 4, 4 halved is 2, and 2 halved is 1. So I could put any number here, okay, and I'd know that in 3 half-lives time it would have gone 2,000, 1,000, 500, 1/8 of the original sample. And then if I told you that the half-life was 1,000 years, you'd be able to say that this radioactive isotope would have fallen from 4,000 to 500 in 1, 2, 3 half-lives. This would have taken 3,000 years. Okay, so like I said, this value for half-life you can take from the graph or be told, and it could be minutes, it could be seconds, it could be billions of years. Okay, and remember your proportions that remain after each half-life.